Okay, let's talk about the section 13.1. It's a chapter 13. Chapter 13. This chapter contains many things. First, sequences. Inductions. And the binomial theorem. The binomial theorem. Three part: sequences, inductions, binomial theorem. The first section, 13.1, sequences. Sequences, well, from English we know it's just a sequence of numbers. So definition, because whenever you talk about a sequence, it has an order, right? 1, 2, 3, 4, first, second, third, last. So a sequence is a function whose domain is the set of positive integers. Right? Like what I said, the first, the second, third, fourth, and tenth. So the first one is a value. When you choose 1 as an input, then you get the corresponding output, right? And then you get the second one, third one. So first, second, third, those are the domains, and the value are the range. For example, let's see, 1, 1/2, 1/3, 1/4. The reciprocal sequence. So it is defined over the integer, positive integers. The first value is 1, second value is 1/2, and the nth value is 1/n. Right? So this is a sequence. Of course, the sequence can be very random. So here we only say it is a function. It's not always evaluation of certain function. It can be very random. For example, you can just randomly say the first number 3, second number 1, third number 4, fourth number 5, 1, 5, 9, 6, 2, 6, 5, 4, something. I mean, I try to recall the value of the pi. So 3.1415926, whatever, I don't remember it. But anyway, the sequence can be also very random. You cannot predict what's next. Okay, so that's also a sequence. Of course, for you, if you define it, every position you know what it is. But if I'm not the person defining it, I don't know what's that. So it can be very random. Okay, if it is too random, then we cannot study it. So of course, when we study the sequences, it must follow some order, follow some pattern. Okay, so 1, write the first few terms. First several terms of a sequence. So actually we did write first several terms. So each number is called a term. Okay, each number is called a term in this sequence. So you may say, okay, if it follows some pattern, we say it is f1, f2, f of 3, f of 4, and so on. If we if we let function fx be 1 of x, the reciprocal function, then the f1 is 1, f2 is 1/2, f3 is 1/3, f4 is 1/4. It's because we know the formula, so we can predict or we can write down the term quickly, right? But if we don't know that, it's just a random function. A function which you may know or you may not know. And sometimes we don't want to write this way. It looks like the evaluation of the function. It's here we want to emphasize we study the sequence. So we may write this way. So a sub 1. A sub 1 means the value of the first term. For example, a sub 1 is equal to 1. A sub 2 is 1/2. This number 1, number 2 are the location, the position. This is a first number, second term. And A3 is 1/3. It's a third term. The third term is equal to 1/3. A sub 4 is 1/4. So we can also write a sequence based on this form expression. Okay? So we can also write like b sub 1 as 1/2, b sub 2 as a 1/2 squared, b sub 3 as a 1/2 cubed, and b sub 4 as a 1/2 to 4th power. Okay, so this is the power sequence. And if you know the expression, you can say, okay, when you let x to be the integer n, you have 1/n. And here a sub n is equal to 1/n. And this b sub n is 1/2 to nth power. And this is called either the nth term or the general term. Nth term means whenever you have a value, positive integer value n, you can determine the corresponding term. Or general term, it also means the same thing. I generally know what is the value of the term for each different position. Okay, so for example, we may write it this way. We use a big parenthesis and we use a sub n. We mean we have a sequence. This symbol just means we have a sequence. And if I write it equal to n minus 1 over n, means the general term a sub n is equal to n minus 1 over n. So this symbol just means this. So we have a sequence, we know the general term. If we know the general term, we can evaluate. We can get the first few terms. For example, a sub 1. What is a sub 1? N is equal to 1. So when n is a 1, it's a 1 minus 1 over 1. 1 minus 1 is 0. 0 over 1 is 0. And then a sub 2 is a 2 minus 1 over 2 is equal to 1/2. A sub 3, 3 minus 1 over 3, it is a 2 over 3. A sub 4 is 4 minus 1 over 4 is a 3 over 4, right? See? So we can evaluate, we can find the first several terms of a sequence when you have the general term. Okay? Second, for example, if we write b sub n, the sequence b sub n as a -1 to power n plus 1 and times 2 over n. Times 2 over n. So this coefficient times this rational number. Okay, now let's evaluate. When n is a 1, so you just let n be 1. So it's a -1 to 1 plus 1 is 2. It's a 2 over 1. -1 squared is 1. 2 over 1 is 2. So it's a b sub 1 is 2. And b sub 2 is a -1. B is equal to 2. 2 plus 1 is 3. And then here it is a 2 over 2. 2 over 2 is 1. -1 cubed is -1. So the product is -1. And then b sub 3. B sub 3, n is equal to 3. So it's -1 to 3 plus 1 is 4. and then it's a 2 over 3. 2 over n is a 3, 2 over 3. Negative 1 to fourth power is 1. 2 over 3 is 2 over 3. And let's continue. B sub 4. B sub 4 is negative 1 to 4 plus 1. 4 plus 1 is 5. Then it's a 2 over 4. Negative 1 to fourth power is negative 1. 2 over 4 is 1/2. Okay? So if you want to evaluate first several terms, you just let n be the first several positive integers, and try to evaluate the expression. Okay? So this sequence, you see, this sequence, you have a positive number, negative number, positive number, negative number. You can expect that the next number will be positive and negative, positive, negative. So if such sequence, if such a pattern appears, this Bn is called alternate. The sequence is called alternate if the sign is a plus, minus, plus, minus, plus, minus. If that happens, we call it alternate. Okay? It's just a name. Later we will see the name. Sometimes the definition of the general term may not be very clear or very simple. Not like this one. It's very simple. Sometimes it's a C sub n. This sequence is n if n is even, and then it is equal to 1 over n if n is odd. So it has a required restriction or the cases. So let's try to evaluate. C1. 1 is odd, so you follow this formula. 1 over 1 is 1. Then C2. C2 sub number 2 is even, so you're going to follow this expression, so you get 2. N is 2, so you get 2. And C3. 3 is odd, so you have to use 1 over n. 1 over n is 1 over 3. C4 number 4, the index n is even, so you follow this first expression, it is equal to 4. And C5, similarly, it is equal to 1 over 5, because 5 is odd. C6, 6 is even, so you use the first expression n, so C6 is equal to 6. This moment, n is 6, so when it is equal to n, it is equal to 6. Okay? All right. So the previous examples just tell us if we know the general term or nth term, we can write down the first few terms. And sometimes we have a sequence in detail. We want to get the pattern from the first few terms. Determine a sequence from a pattern. For example, the first one. The first one, we get e squared over 2, e cubed over 3, e to 4 over 4, and dot, dot, dot. Well, the first one is e. Second one, e to 2 over 2. Third one, e to 3 over 3. Fourth one, e to 4 over 4. So what is a sub n? A sub n, you can say it is e to n over n. For whatever position, this is the second position is 2. Third position is 3. Fourth position is 4. So nth position is n. So it's e to n over n. Right? Second, if we have 1, 1 over 3, 1 over 9, 1 over 27, and dot, dot, dot. Well, we have to be alert. You see here you have 3, 9. 9 is a 3 squared. 27 is a 3 cubed. 27 is 3 cubed. Here, you don't have the denominator. You don't have the denominator. You can consider it as a 1 over 3 to 0. Okay? So the first position, you have 0's power. Second position, you have first power. Third position, you have a square. So if you have a nth position, you actually have a little shift. Nth position, here, this is 0. It corresponds to the first position. 1 corresponds to position 2. Square corresponds to position 3. So there's a shift. So it's n minus 1, an index shift. Okay? So you have to observe the pattern from those numbers. Okay? So we have 1, 3, 5, 7. Well, it's a sequence of odd integers, right? It's a sequence of odd integers, 1, 3, 5, 7, 9, 11, 13 stuff. Odd number, how do we know the odd number? Odd number means it's not the multiple of 2, right? It's not a multiple of 2, it's odd. If it is a multiple of 2, it's even. So even numbers, it's easy to describe. What is even number? 2 times n. Whenever you have a factor 2, it's even. But now it's odd. So you can either plus 1 or minus 1 in order to get an odd number. You have an even number, on 2 sides you will have odd number. Then in this place, you use plus or minus. Which sign do you use? You plus 1 or minus 1? It depends on the pattern. You see, when n is a 1, 2 times 1 is 2. In order to get a 1, you have to minus 1. 2 minus 1 is 1. When n is 2, 2 times 2 is 4. 4 minus 1 is 3. When n is 3, 2 times 3 is 6. Minus 1 is 5. Right? So we know we start from the even number. We subtract or add a 1 to get an odd number. So which operation do you choose? Addition or subtraction? It depends on the adjustment. You want to know it fits the property. So you try. If the addition works, then you use addition. If the subtraction works, you use the subtraction. Okay? So for example, let's create one formula. It's called C prime. C prime, if we write this way, 3, 5, 7, 9 stuff. It's also a sequence of odd integers, but we don't start from 1, we start from 3. In this case, we have an even number, 2n. When n is a 1, 2 times 1 is 2, but we need 3, so we have to add 1. See, this time you have to do the addition with 1, because 2 times 1, the first number, 2 times 1 is 2, plus 1 is equal to 3. Okay? Exercise D, 1, 4, 9, 16, 25. Well, what is the pattern of those numbers? 1, 4, 9, 16, 25. It is 1 square, 2 square, 3 square, 4 square, 5 square. It's a perfect square. So you get d sub n equal to n square. This is the first number square, second number square, third number square, fourth number, fifth number square, fifth integer square. Okay, so it's exactly n square. Okay, so it's a 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over 7. So it's a reciprocal number. But the problem is it's alternating. It's a plus, minus, plus, minus, plus, minus, plus, minus. We expect it is alternating. Alternate sequence, how do we get an alternate sequence? From this example, we see that if you have -1 to certain power, you will have plus or minus. So I'm going to put a -1 to certain power. To what power? If I put n there, when n is equal to 1, you have a negative sign. But the first term does not have negative sign, so you use n plus 1. N plus 1, when n is 1, n plus 1 is 2. -1 to 2 is positive, so there's no negative sign. So let me write it clearly. So the exercise E, example E has a general term -1 to the power n plus 1 times 1 over n. So this kind of a problem is sometimes a little bit tricky because you have to observe the pattern from some limited information, from a few terms. You do need to find the relation, and that determination should depend on the integer. You see, it is a 2 square, 3 square, 4 square, 5 square, 1 over 2, 1 over 3, 1 over 4, 1 over 5. If that relation is not related to the integer, then it is useless. Okay? Remember, if it's not related to the integer, then it becomes useless. You have to have the integer input, and the integer is the position number. Okay? In the sequence study, there is a very interesting, useful sequence. It's called a factorial symbol. What is a factorial symbol? We want to study the product of integers. So for n greater than or equal to 0, n is an integer. The factorial symbol, n factorial, is defined as follows. N greater than or equal to 0, n can be 0. When you have a 0, 0 factorial, we define it to be 1. Okay, it's just definition. And then 1 factorial, we also define it to be 1. And if n is greater than 1, start from 2, then n factorial, what is n factorial? You just get the product 1 times 2 times 3 up to n. So you get the product of first n integers that is defined to be the n factorial. Okay, that is defined to be n factorial. For example, if you talk about 2 factorial, 0 factorial, 1 factorial, they are defined separately. But if you have an n factorial, you have this general formula. 2 factorial means 1 times 2. You just get the first 2 integers and do the product. Then 1 times 2 is 2. So 2 factorial is equal to 2. 3 factorial is 1 times 2 times 3. 1 times 2 is 2. 2 times 3 is 6. 4 factorial, 1 times 2 times 3 times 4. Okay? It's equal to 24. Why? So 1 times 2 is 2. 2 times 3 is 6. 6 times 4, 24. 5 factorial, 1 times 2 times 3 times 4 times 5. Actually, you see here, this is a 4 factorial. 1, 2, 3, 4. You have the product. It's 4 factorial. And it's a 24. 24 times 5 is 120. And 6 factorial, 1 times 2 times 3 times 4 times 5 times 6. And here you know this product is 120. You just compute it. And then times 6 is 720. And so on. You can continue this product. Okay? So this is a factorial symbol. And you continue this, you will get 7 factorial is 5,040. And 8 factorial is 40,320. whatever, the number will increase very, very fast. But just keep in mind, we have this n factorial symbol. It means the product of the first n integers. And from this observation, you see 6 factorial is actually 5 factorial times 6. So n factorial is actually n minus 1 factorial. It means you pick up the first few terms, you do the product, and then you get n minus 1 factorial, and times the last integer, times n. Okay, n factorial is n minus 1 factorial times n. All right. So this is the factorial symbol. The factorial symbol. The factorial symbol, you see here, the n minus 1, this number, it depends on the previous input. It's the previous term with the additional multiplication. So the second part of this section, write the terms of a sequence defined by a recursive formula. By recursive formula. So what is a recursive formula? So let's copy the long definition. It's not exactly a definition, it's like the explanation. So a second way to define a sequence is to assign a value to the first or first few for all the first few terms and specify the nth term by a formula that involve one or more of the terms preceding it. It's called, it is said to be defined recursively. The rule, the formula is called a recursive formula. It's called a recursive formula, okay? So let's see how do we understand this. For example, let's follow the sentence and do this example. We first define S1 equal to 1. And second, we get Sn is equal to n times Sn minus 1. Okay, S1 is 1, Sn is n times Sn minus 1. Now let's write down the first few terms. So for example, S1 we already know. Let's talk about S2. S2 is, you see, n is 2. So 2 times S2 minus 1 is 1. So 2 times S1. S1 is 1, so it's 1 times 2. It is equal to 2. Okay, Then let's talk about S3. S3 here, n is a 3, so here's a 3. S3 minus 1 is 2, so it's a 3 times S2. S2 is 2. S2 is a 1 times 2. So you just multiply this, the previous line by number 3. So it's equal to 6. Here, 1 times 2 is a 2 factorial. 1 times 2 times 3 is a 3 factorial. If we continue this, S4 by this formula is 4 times S4 minus 1, S3. So it's 1 times 2 times 3, this is S3, and times 4. It's a 24, it's a 4 factorial. And from those 3 verifications, we see that this recursively defined sequence, so Sn is actually equal to n factorial, the product of the first n integers. Okay, so you got S2, 2 factorial, S3, 3 factorial, S4, 4 factorial. If you do more practice, you will see S5 is 5 factorial, S6 is 6 factorial. Okay, so this one is a recursive formula. I mean, this one is a direct formula, right? A direct formula. You have the general term. So the difference between the general term and the recursive formula is that if you have a general term, you just plug in n, you can get the answer. But if you only have a recursive formula, you want to find, for example, I want S100. Then you have to find S1, S2, S3, S4, S5 until S99, and then you can find S100. Okay? So in order to get get the value for some large n, you have to know all the previous values. So that's a disadvantage. Advantage is that sometimes this relation is easier than the general term. So we can find this relation first and may or may not be able to find the general term. Okay? Next, so we say the U1 is equal to 1, U2 is equal to 1, and U sub n is equal to Un minus 2 plus Un minus 1 for n greater than or equal to 2. N greater than or equal to 3, n greater than or equal to 3. Okay, this is also a recursively defined sequence. The nth term depends on the preceding two terms. Two preceding terms. Well, let's just try it, because you already know U1, U2. Let's talk about U3. U3, n is a 3. N is 3, then n minus 2 is a 1. N minus 1 is 2. So U3 is U1 plus U2. U1 plus U2 is 2. 1 and 2. And U4, n is 4. 4 minus 2 is 2. 4 minus 1 is 3. So it's a U2 plus U3. So you have 1 plus 2, you have 3. So let's see. The first position is 1, and second number is 1. You add these two, you get the next number. You add these two, you get next number. Add these two numbers, you get next one. Add 3 and 5, you get 8. Add 5 and 8, you get 13. So this is the pattern how you get the U sub n based on the preceding terms. Right? Yeah. Okay, so here you have to be careful. You choose n, this place n as a 3, then this right side n is also 3, but n minus 2 becomes 2, n minus 1 becomes a 3. Okay, so that's the pattern. And this sequence is very, very famous. It is called the Fibonacci sequence. The Fibonacci CCI sequence. It's this long sequence. is called Fibonacci sequence. Each term is called the Fibonacci numbers. So all the numbers are called Fibonacci number. Okay. So this is a sequence. When we have a sequence, of course, there's an interesting, the natural operation. We want to add them together. For example, you have salary. You work, you have salary. January, February, March, April, May, June, up to December, you get 12 times salary. And you want to count the total, so you're going to add those numbers together. Okay, so use summation notation. Okay, so we possibly want to say, okay, let's add the salaries of all 12 months. Okay, so you're going to write this very, very long sum. Of course, if you get paid every 2 weeks, you have to add 24 numbers. You're going to copy it. If you get paid every week, you will a year possibly you will get 50 numbers. You're going to write up to A1 plus A2 plus A3 up to plus A50. It's too long. We don't want to copy it that way. So we have such following symbol. You see here, you do not miss any term. You really get 1, 2, 3, 4 up to 12. You do not miss a term. So we use the following symbol. We put a sigma. Sigma means you're going to do the sum. And this index we use I. The index starts from 1, stops at 12. And the index appears as a sub-index. So this symbol just means you're going to add one. Index is 1, is the first term, and then index becomes 2, and you get A2. Index 3 is A3. Index is 12, you get A12, and you add them. So this symbol means this very, very long sum, long expression. And this is called the summation notation. Summation notation. Okay? This is called a summation notation. We use sigma, this symbol to represent, we want to add a few terms. Okay? So for example, if we say we put sigma I from 1 to n, 1 over I, what does this mean? It means you first let n be 1, 1 over 1 is 1. And second, n becomes 2. You do addition. 1 over 2 is 1 over 2. And then you let n be 3. Every time you increase n, increase index by 1. Every time you do it. And 1 over 3. And 2, when the index becomes n, you add up to 1 over n. You use dots, of course, because n you have no idea. You don't know how when you stop, so you just write the dots. So this sigma notation just means the sum of the first n reciprocal numbers. Okay? The other one? K is from 1 to n, k factorial. K is a positive integer, so we can talk about the factorial. When k is 1, it's just 1 factorial. Okay, you do the evaluation at 1. You finish it and add, you let n be 2. 1, 2, 3, 4. It's always the integers. It's 2 factorial. And then next, the 3 factorial. Until you get n factorial. You add all those numbers together. So 1 factorial plus 2 factorial plus 3 factorial plus up to n factorial. Okay? So that's the example. If you have a sigma notation, how do you expand it? Like you make this a short notation into a long notation. And sometimes you have a long notation. You want to write it in the compact form. So, for example, if you have 1 square plus 2 square plus 3 square plus 4 square up to plus 9 square. You see here we use dots to save 5, 7, 8. 5, 6, 7, 8. Yeah, 5, 6, 7, 8. I don't want to copy something. It's already very long. So how do we simplify it? We first put a sigma. Sigma only covers the positive plus sign. It does not cover negative sign. Negative sign, you have to handle it by yourself. And sigma, this pattern is a 1 square, 2 square, 3 square, 4 square. So it's a k square. K, it starts from the first index 1, stops at index 9. So this long sum can be written as sigma k from 1 to n k square. This letter k is up to you. You can choose I square, you can choose A square, you can choose L square, whatever. If you change this number, for example, this one, this is also the same expression. Just use a letter I instead of a K. But when here you use I, here is I, because these two numbers are the same thing. Or you can use whatever number whatever symbol you like. Okay, this is also correct. The letter is not important. The expression is important. Okay. Okay, next one. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/2 to n minus 1. Okay, so this is a general term. 1/2 to n minus 1, or the nth term. Then what is this? So it's a 1/2 to I minus 1. I is from 1 to n. When I is 1, 1 minus 1 is 0. 2 to 0 is 1. 1/1 is 1. When I is n, it's the last term. So it starts from 1, stops at n. You choose the index letter I. Okay, so that's writing a sum in the summation notation. All right. Well, so here we just write it in the compact form. We don't compute it. It's just a way to write the long sum. It's not a way to evaluate. Here, I still don't know what value it is. If you have no other formula, you really have to write them one by one and square each of the integers and add them together. This is an art. It just makes your writing better, but it does not make your computation better. Okay? For this writing, let's try to find some sum. We are not just artists. We want to find, we're mathematician. We want to find the sum. Find the sum of a sequence. Some sequence. Not every sequence we can find the sum. Just for some sequence. And of course, if you fix it, for example, if you have 1,000,000 terms, you just do it by hand. You can compute it. But here when we say find a sum means we are going to get a smart, quick formula to get the sum of a few special sequence. Okay? So first, let's try to study the property of this sigma notation. Sigma notation has the following property. For example, you have AK, k from 1 to n. You have A1 plus A2 plus A3 up to plus AN. And then every term, you multiply it by C. What does this mean? It means the first term is A1, you multiply it by C. Second term is A2, you multiply it by C. third term is A3, you multiply it by C. So every term you multiply it by C. Okay, you do multiplication with C. Since all the terms have the common factor C, we can factor it out. Then we will have A1 plus A2 and plus A sub n. And this long sum is or can be represented as a sigma k from 1 to n ak. Okay, so what does this mean? This means if you have a constant number, constant means it does not depend on the index. For every point, you have the same number. If you have a constant coefficient, you can move it forward. You see, you move C from inside to outside. The constant coefficient can be moved forward. That's the first property. Second property, if you have AK plus BK, for example, A1 plus B1, A2 plus B2, A3 plus B3, A4 plus B4, you have those paired and you do the sum. It is equal to, you can add AK first and BK second, and then you add those two results together. Okay, so this is of course correct. It's like you regroup them. You get all A terms together, all B terms together, and then add each part separately, right? So that's correct. It's a sum rule. And then we have the same thing, the difference rule. A sub k minus B sub k. Okay, let me write it quickly. It's A1 minus B1, that's one thing, plus A2 minus B2, the second one, plus A3 minus B3, that's the third one, right? And then how do you do that? You can move A1, A2, A3 together, and B1, B2, B3, they all have subtraction. So you minus B1 plus B2 plus B3 with a parenthesis, right? You minus the sum of them because they all have the negative sign. And this is a sigma of AK minus sigma of BK. So it's a sigma k from 1 to n AK minus sigma k from 1 to n and BK, the difference rule. So we say the constant coefficient rule. Constant coefficient rule, sum rule, difference rule. Okay? And what else? What else? See, A1 plus A2 plus up to, let's say, a million. No, not million is too big. Let's do 100, up to 100. I can do the following thing. I first add 49 numbers together, and then start from 50, I add up to 100. Right? So we add these 49 terms together and these 51 terms together. So the first row can be written as a sigma I from 1 to 100 AI. And then this part can be written as a I from 1 to 49 A sub I plus here I from 50 to 100 plus I. You can just cut the long sum into two parts, right? So once you cover all the terms, that's fine. I don't care if you compute the first few terms and other terms separately and then add them together. It doesn't matter. Okay. So the fourth property is a general writing of this. So you have I from 1 to n AI equal to I from 1 to j AI plus next one, I from j plus 1 to n ai. You can stop at any position. You compute the first few terms and compute the rest of the terms, add them together. Okay, so that's what it means. And in the book, they write this formula. This is a simple observation. They write this formula in a different way. How do they write it? They move this to the other side. So they get the last term is equal to the difference of them. Okay, so you move this term to left side. I from 1 to n, I from 1 to j. The difference is from j plus 1 to n. You basically just remove the first j terms, then you count the summation from the j plus 1's position. J plus 1's position, right? You have n positions. You remove, subtraction means you remove the first j terms. You start from j plus 1 and you stop at n. The same thing, that's the same stuff. Okay? So just keep in mind, the sigma notation is a fancy notation, but it just gave us a short writing about a long sum. So whenever you can understand the sum, you will understand the sigma. It is not about the evaluation so far. It's not evaluation. Okay? So here we have those 4 general properties, basic properties. Okay, so the constant coefficient rule, sum rule, difference rule, and here you remove the first few terms, you start from j plus 1 to n. Be careful, here is a j plus 1, here is j. Okay, so again, the sigma notation is just a notation, it's not evaluation. But we do want to evaluate some special sequence. So here, the next theorem just give us the value of certain sigma notation for certain special sequence. The first one, for example, the sigma of a constant number, k from 1 to n. So first of all, what does this mean? This means when k is 1, you have this constant number. When k is 2, you have this constant number. When k is 3, you have this constant number. When k is n, you still have the constant number. So you will have n copies of the constant number c. N terms of a constant number c. N terms of constant number c, by the definition of the multiplication, it's c times n. Okay, you see, that's a very, very, very special sequence. It's a constant sequence. Nothing changes. It doesn't matter what position you have, you will always have this constant number. So it's a special sequence. For this special sequence, sigma k from 1 to n of c is equal to c times n. This n means you have n copies of a c. You have n copies of c. Okay? And next, sigma k from 1 to n k. Let's first write a few terms. When k is 1, k is 1. When k is 2, the value k is 2. When k is equal to 3, the value k is 3. When k is 4, the value is 4. And until you stop at n. So this symbol actually means the sum of the first n integers. This is a sum. Factorial means a product. They're different, okay? They are totally different. Here is a sum. The sum of the first n integers, we have the formula to compute it. The sum of the first n integers is equal to n times n plus 1 over 2. For example, let's just try the simple one. For example, let's just add the first 5 integers. From the formula, let's predict n is a 5. So it's a 5 times 5 plus 1, 6 over 2. 5 times 6, 30 over 215. Now let's compute. 1 plus 2, 3. 3 plus 3 is 6. 6 plus 4, 10. 10 plus 5, 15. So it's good. So this formula at least correct for this case. Well, it's correct for all the integers. You can try. Okay? So the sum of the first n positive integers is equal to n times n plus 1 over 2. Okay? This is also a very special sequence. And the next special sequence, k from 1 to n, k squared. It is 1 square, 2 square, 3 square, n square. The formula is n times n plus 1 times 2n plus 1, 2n plus 1, n times n plus 1 times 2n plus 1 over 6. Okay, the video will stop soon. I will stop this video and continue in next video. Okay.